Calculus is the first time we get to work on optimization. We talked about this scenario from the beginning of, it's like the first page of chapter 4 in your textbook. What if you had a function that told you what gas mileage you got as a function of how fast you drove your car? You would want to figure out what speed you should drive, what velocity you should drive to get the best gas mileage. Because you want to have the best gas mileage, you want to save money, you want to save fuel. So this word best, it's what we call a superlative word. And it's the clue that we're talking about an optimization problem. If you want to pick an input because it's going to give you the best possible output, that's optimization. So other superlative words that you'll see in problems that are your signal that it's an optimization problem: best, least, fastest, furthest, slowest, longest, highest, greatest. Those are all examples of superlative words, and your sign that we're talking about an optimization problem. So we talked about this back at right before 4.1. We could graph this function if we have it and try to figure out what the highest possible gas mileage is. We'd be looking for the highest point on the graph, which is somewhere about there. So can we use an algebra way to find that highest point? Because maybe we don't have a graphing calculator. Maybe we don't have an exact function here. We only have other, maybe not a formula for the function, but some other information about it. How can we figure out where we get what velocity to drive in order to get the best gas mileage? Okay, so an optimization problem, it's an application of derivatives, and it's definitely going to be on the AP test, and it's a real world problem that would give you a reason to find an absolute minimum or an absolute maximum. So we said absolute minimums and absolute maximums. We can call those absolute extrema or global extrema. And we practiced that in 4.1. We made a t-chart with all the endpoints and all the critical points, and we used those in our function to figure out which one gave us the highest value or the lowest value. That's what we're going to do here. We just have a scenario where we're going to apply that process to. Okay, so the key to an optimization problem, we're going to use that chart. We're going to talk about my 7-step method, only 7 steps. We're going to talk about that chart, remembering that in your t-chart, the input values that you need to test are endpoints and critical points. And remembering that critical points can occur where the derivative of the function you care about is 0, or the derivative of that function is undefined. Okay. These are steps I like. You certainly don't have to memorize the steps. We just kind of need to get used to this process. But as you're starting, these are the things we're going to look for to help you kind of get used to this process of answering an optimization problem. So number 1, you have to figure out what you're trying to optimize. Maybe it's velocity, maybe it's income, maybe it's speed, maybe it's whatever. So sometimes that's a tricky thing in the problem, is to figure out exactly which quantity you're trying to optimize. And you want to try to figure out, are you trying to find a maximum or a minimum? You might want to maximize income, but you might want to minimize cost. So make sure that you're keyed into which you're looking for, minimums or maximums. Once you decide the quantity you're trying to optimize, you need a function for it. And this only works if we're talking about functions in one variable. So sometimes there's some creative algebra you'll have to do to make it so your function has only one variable. We're going to use that function to find critical points, because that's what we have to check. We're going to have to check endpoints and critical points. Once we have those critical points and any endpoints that are either implied by the problem or specifically given, we're going to make that t-chart with the inputs that we found, endpoints and critical points, and the outputs for that quantity that we were trying to maximize. And we're just going to look in the list for the biggest or the smallest, depending on what you need. output value. All right, so let's try that with a problem here. Oops, that's me. Oh, so quick before we do this. The output, the y value, that's the maximum or the minimum. Sometimes a problem won't ask for that maximum or minimum value. It'll ask for the x value where it occurs. So just make sure you can tell the difference between which one you're looking for. It's going to be the same row in your t-chart, but make sure you give the maximum value, the y value if you're asked for it, or give the location, which would be the x value. All right, so here we go. I want to find the maximum acceleration of a particle, and I know the velocity of the particle. So this is an optimization problem. They've said maximum acceleration, so I didn't even have to think too hard about that. And what is it that I'm trying to maximize? I'm trying to maximize acceleration. All right, so step one, we're going to try to maximize acceleration. So I'm going to need a formula for acceleration. Well, here, it's not too tough. I've been given the velocity, and I know that acceleration is the derivative of velocity. So the quantity I want to maximize is acceleration. So I'm going to take the derivative of velocity, and now I have my a function. A of t is 3t squared minus 6t plus 12. Step 3, find the derivative of that function. So that would be a prime. A prime here. So my v and my a weren't too tricky. They were just polynomial functions. So finding a prime of t, not so bad. 6t minus 6. Step 4, I need critical points for my a function. That's going to be any place where a prime equals 0. So whatever you're, I need my a prime to equal 0, so I need 6t minus 6 to equal 0. If you solve that in your head, that's fine. If you want to add 6 to both sides and divide by 6, it doesn't matter here how much work you show. You need to get to the place where you decide that t equals 1 is the critical point. So recall that a has a critical point anytime a prime is 0, which is where t equals 1, or where a prime is undefined. But notice a prime is just a linear function. There's nothing about it that would make it impossible to use any particular input value. So here I have my t-chart. I'm ready to make my list. So I said in my t-chart I'm going to need endpoints. I was given 0 and 3. I'm going to need to use any critical point. I got a critical point, t equals 1. So I'm trying to maximize acceleration. I found critical points for acceleration and the endpoints for my acceleration. And now I'm just going to compute the acceleration at those input values. I'm really going to pick the result that's biggest. Here, I was asked to find the maximum acceleration. So I'm going to pick the number from the A column. If I'd been asked to find the time at which the maximum acceleration occurred, and pick the t value that goes with it. But here we go. Here's my. Don't let that fool you. Sometimes you're used to just going back and plugging back into the original function, but that's not what's going on here. I'm trying to find the maximum acceleration value, so I'm going to use these t values in the acceleration function. Here's acceleration. So a of 0 is going to be 12. A of 1 is going to be 3 minus 6 plus 12, which is 9. And I'm going to need a of 3. That's going to be times 9 is 27 minus 18 plus 12. I just have to figure out, is that bigger or smaller than 12? That's 9 plus 12, which is, move me out of the way, 21. That's the biggest number in my list. I don't have to check any other t values because I've checked both endpoints and any critical points for acceleration. The maximum acceleration achieved by that particle whose velocity was given is 21, and it happens at time equals 3. All right, here's another one. This is not a super exciting scenario, but imagine I know that y is equal to 2x minus 8. What is the minimum value of x times y? This is an optimization problem. I see here minimum value. They weren't very subtle about it. So I'm going to go through my process. The quantity that I want to, in this case, minimize is the product, so the multiplication of x and y. So what I'm, look at that error right there. We want to minimize the product of the two variables x and y. So I'm going to do my best to write a function for that product, write an expression for that product that only contains one variable. So that's going to take a little bit of work because right now I have two variables, x times y. So here, not so bad, watch what I do. I'm going to make a function p, and it's going to be x times y. But I know that y is equal to 2x minus 8. So everywhere I see y in that rule, I can replace it with 2x minus 8. Now I have one variable. I've distributed the x just to make it easier in the next step to take the derivative. Because that's going to be step 3. I'm going to need a derivative for p. I picked the letter p to stand for product just to kind of help us remember, because that's the quantity we want to minimize. Okay, so my p prime, not too bad, 4x minus 8. My next step is going to be to find out where p prime is undefined. Never, right? Because p prime is just linear. And find out anywhere where p prime equals 0. That's going to happen when x equals 2. So now I've got my I'm ready to make my chart. Okay, so here there is no limit imposed on either x or y. So if this were a real world scenario, I might have a real world constraint that I'd have to consider adding, but none have been given. All I know about x and y is that they're numbers, so there's no minimum or maximum number I could use. So the only option, the only point that I have to even test is going to be when x equals 2. So I'm going to do that. I'm not getting a super free pass. I'm still going to have to convince myself that this is really a minimum. But I'm going to use 2 for x in the p of x function. That's going to be 2 times 2 squared minus 8 times 2, which is 8 minus 16, which is negative 8. So to convince myself that that's the smallest value and not, for example, really the biggest value, I can test any other point on this graph that I want. Take any other x you want. You could let x equal 0. What if I let x equal 0? Then this is going to be 2 times 0 squared minus 8 times 0. Is negative 8 still the smallest? Negative 8 is still the smallest possible product. So I conclude that negative 8 is the minimum value of the product of x times y.